So it's the time to start the event. So I welcome you on behalf of St. Joseph Institute of Technology. I am Dhanush Ganesh from AAA Department. I welcome Mr. Sriraj Sir, Director of MCOG Solutions, Chennai. So welcome you, sir, for this event. So the topic of the webinar is design of digital audio playback system using AT89S51 Microchip Family. I think everybody likes music. So music system by our own makes us so fun. And here we go for into the webinar for today's session by Mr. Sriraj sir. Sriraj sir. Sir, thanks a lot for accepting our invitation for the webinar. So you can start and proceed your session, sir.
Yeah, thank you so much. So before I start with, let me make sure that you are able to see the screen as well as my voice is clear.
Yeah, yes, sir. I'll be checking it, sir.
Please check and let me know.
Yeah, yes, sir. Yes, sir. The slide is visible.
Okay. Right. Okay, let's start. So I welcome everyone for this wonderful session on design of digital audio playback system. Myself, S.P. Sriraj, Director of MCOG Solutions, Chennai. And MCOG Solution is a very small company. It's a product development company which develops product in line with the engineering curriculum. And we don't like plug and play type of training. We always motivate students to develop their own products which lies in the curriculum. So that means you have to learn your curriculum properly, and you will be able to design a lot of commercial products by your own. So that's how we used to give training, and we used to motivate students to develop products. So you might have, some of you of SDIT have designed inverters from our training, which was held in way back in 2019. And somebody has attended a solar on-grid system and design. So basically, the training motivates you to develop products. That's the importance what we give to the curriculum. So today what we are going to see is we are going to design a digital audio playback system using embedded systems. So first of all, I want to tell you what is this digital audio playback system, or what this playback system in the sense. For example, if I have a song here, okay, I have an MP3 song. This is a clip, waveform clip of an MP3 song. What we can do is we can store this song somewhere, and we can reproduce this song. So finally, this is the reproduced song or reconstructed song. You can see the similarity, both looks to be same, right? So what we try to do is we try to take one song, we make it into samples. Okay, one song will be converted into just numbers, and that numbers we will take it into our programming softwares, and then write coding and develop the same pattern of waveform. So what is the use? You can store any song in that system, and whenever you want to play back it, you can play back it later. So the idea is we have original MP3 song, we convert this song into numbers, some random numbers, and then we write some coding in order to reconstruct the same waveform whenever it is required. That means whenever you are wish to hear the song, you can reconstruct the song. Now, how do we do it? We use a kind of software as well as programming, and use a microcontroller. Okay, so we use a microcontroller called AT89S51, and we use some software support called Microvision 5, and then we do some kind of programming and convert the original song, which is being converted into numbers, and then finally into the same pattern of waveform. So that's the idea of digital audio playback system. So it's a playback in the sense you store it and play back again whenever it is required. So that's the idea of today's session. And to know or to develop this digital audio playback system, it's not a better idea to go and teach you how to develop this audio playback system, rather than we have to go from scratch, right? We have to understand certain basic concepts. We need to understand basic idea of programming. We need to develop some small coding, and then we need to develop a waveform, and finally we'll try to have the final audio playback system. So I have planned something like this. The agenda for today's session looks to be like this. First, we learn something about digital systems, and then we go ahead to understand what are the software tools are available in the market to develop this product. And then we go ahead and we construct a sine waveform. Okay, I'm going to construct a sine waveform through numbers. You have some numbers, that's it. But through those numbers, we are going to develop a sine waveform. And then we will try to develop some music tones. You will be allowed to hear a lot of music tones like keyboard tones or maybe sari gamma padani, whatever it is, all tones. So how to develop those tones through coding. And finally, we enter into a demo of playback system with a number of samples. Okay, so this is the plan, what we are going to do. We will make this session in such a way that you will be able to understand concepts very clearly, and you will be able to interpret what I am actually doing to develop this product. Okay, so let me go ahead with the basics. So what exists in the nature, or what God has given to us, is nothing but some kinds of measurements. So what is some kinds of measurements? Some kinds of measurement is nothing but mass, length, time, temperature, humidity, and so on, right? So we call that as physical quantities. So what God has given to us, or what exists in the nature initially, is nothing but some kinds of measurements called as physical quantities. Can be temperature, can be humidity, can be mass, length, time, everything which you can measure, right? Now, what is engineering? What is engineering? From simple electronics to artificial intelligence. If you ask me what is engineering, engineering means creating purposeful utilization of these measurements. In the sense, God has given you certain measurements in your hand, like what I said, temperature, humidity, mass, length, and time. Now, as an engineer, what you are going to do is you are going to create some purposeful utilization, or you are going to utilize those measurements in some way. Okay, so I'll repeat. Engineering means creating purposeful utilization of these measurements. Measurements in the sense what God has given to us, nothing but the physical quantities such as temperature, humidity, mass, length, time, etc., and so on. Now, what is this purposeful utilization? We are going to utilize these measurements for some purpose. Okay, so what I'm going to do is, I have one guy here. Now I'm asking this guy, okay, what is your purposeful utilization you are going to do with measurements? That means God has given you some measurements. What you are going to do with this? Or what is your purposeful utilization? Or what are your purposes? Now he says, okay, I'm really happy God has given me a lot of measurements. So my purposes are these. I want to measure temperature. For example, let us consider a physical quantity, temperature. I would like to measure temperature. I would love to monitor temperature. I would love to store temperature. I would love to process temperature, control temperature, analyze temperature. And these days, I'm really happy and lovable to steal kind of datas, right? So in the sense, what this purposes means, some people would like to measure temperature. If you, for example, if you take the measurements what God has given, we'll take temperature. Temperature as one of the physical quantity what God has given to us, right? So if you take temperature, some people will love to measure temperature. Why we measure temperature? For example, if you take air conditioner, we love to measure temperature, right? Because we need to control the room temperature. Some people love to monitor temperature. If you go to Coimbatore bus stand, you could see a display where you will be able to see the temperature of any instant. Okay, but they are not going to control the whole Tamil Nadu, whatever it is. Just monitor the temperature and display the temperature. And some people would love to store temperature. For example, if you go to NASA website and ask like January 13th, 1950, what is the temperature? It says, because it would have stored the data, or it would have stored the temperature. And some guys in the automation industry, they take temperature as one of the parameter for their process, right? So we used to process temperature. And sometimes we used to control temperature. Obviously, in an air conditioner, we are going to control temperature. Some people would love to analyze temperature. what we do with analyzing temperature. For example, if you take NASA website and if you ask what is the temperature between 1950 and 2000, it give you a lot of data, and there you can interpret, okay, what is the average rise in temperature every year. So that means you'll be able to analyze the data. And sometimes people would love to steal data, right? These days people are really, focusing only to do these activities and this activity, right? So God has given you certain measurements or data, whatever it is, and we have lot of purposes with data, right? Some guys want to measure data, some guys would love to monitor data, store data, process data, and so on. So to achieve his purposes, these are his purposes, right? To achieve these purposes, what we need is, we need some technology. So technology begins here. Why technology begins, or why technology is required? Because the reason is, we have lot of purposes to do with. What purposes we want to do? We want to do the purposes what God has given, right? So in the sense, technology begins to implement the purposes of human being with the measurements given by God. So technology begins from here. Now, if you see the technology flow, it starts, everything has started from physical parameters, as I said, what God has given, then slowly into voltage and current. Because the reason is, if you want to measure the temperature of a hot box or hot stove, you will not be able to keep your hand on the hot stove and say, oh, this is the temperature right now. This is highly impossible, right? So we were thinking to convert everything what God has given into a quantity which is measurable to us. So that is nothing but current and voltage. That's how we were discovering the current and voltage. After current and voltage was discovered, we thought of having some equations to connect the current and voltage. That comes Ohm's law, Kirchhoff's law, Maxwell's equations, and so on. And after discovering a lot of laws, we got something called RLC components. So after laws, we discovered RLC components. For example, if you take Ohm's law, B is proportional to I. If you remove the proportionality, you get R constant, right? So that means R is a factor which comes from Ohm's law. So that means after the implementation of all these laws, we got to know, okay, these are some basic elements exist in electric circuit. So after discovering all these RLC basic components, then we got to develop something, a wonderful device which is called as transistor. So before transistor, there is something called before transistor and after transistor. The life was amazing. So after transistor, what has happened is, the whole world has divided into two major worlds. One is called analog world, another one is digital world. So the invention of transistors, made everything, in a tremendous journey of digital world as well as analog world. So we have started from what God has given, and we ended up with a highly sophisticated technology called analog technology as well as digital technology. But in this webinar, we are going to focus more on digital world. Okay, so in the sense, the digital world, in the sense, we would have studied a lot of digital ICs, but we are not going to see those ICs. Rather, I'm going to give more importance to something called as a microchip or a microcontroller. Okay, if you see microcontroller in the market, there are a lot of microcontrollers are available, right? So it was developed by a lot of manufacturers across the world. For example, Texas Instruments is one of the major company develops microcontrollers, microchip, analog devices, Cypress Semiconductor, and so on. So a lot of companies are there where they are developing microcontrollers for different applications. And in this webinar, we give more importance to microchip microcontrollers. Now, I'll tell you why I have picked microchip microcontrollers, because of various reasons. And if you would like to see what microchip is doing, you can visit the website www.microchip.com. And you have a doubt like, sir, there are a lot of microcontrollers. If I study microchip microcontrollers, whether the coding can be replicated to all the other microcontrollers, it is not possible. Each of the above microcontrollers over here have an unique instruction set and register set. So therefore, they are not compatible with each other. That means if you are writing coding in a microchip microcontroller, that coding cannot be replicated to any other microcontroller family of any other manufacturer. It is not possible, because the reason is each microcontroller of each manufacturers will have unique instruction set and register set, so that will not be compatible. But the logic you use in one microcontroller can be used to write coding for other microcontrollers. That is possible. So whatever the logic you develop in writing coding with one kind of microcontroller, that logic, the same logic can be replicated to write the coding in any other microcontrollers. That's the reason why we always insist the students to learn at least one manufacturer's microcontrollers, so that it will be very easy to write coding in any other microcontrollers exist in this world. Okay, now why we pick microchip microcontrollers? Because Microchip is one of the leading microcontroller manufacturers in the world, and they have applications starting from toys and up to satellite applications. So they have ICs to make toy as well as till satellite applications. Now, if you go and visit their website, you can see applications every field you can imagine, from let's say from aerospace and defense and up to wireless connectivity. These are the applications. I mean most of the applications are covered by Microchip. So they have ICs for all the applications whatever I'm mentioning here. So that's the reason why we pick Microchip. And another reason is they have good forum help, where if your doubts will be cleared, so that helps for a designer while writing coding. And what criteria embedded system engineers consider in choosing an MCU? In the sense MCU, in the sense microcontroller unit or microcontroller. Okay, so for example, you are an engineer, you wanted to do a project. Now you don't know what microcontroller should you choose, right? So there comes a confusion. How do I choose a microcontroller? I'll give you three simple way to to identify what microcontroller or how you have to choose a microcontroller. The first thing is you have to make sure that your microcontroller or the microcontroller which you are going to pick should meet the computing needs of the task. In the sense, sometimes you would love to make a calculator. For making a calculator, obviously you need a lot of computing task. But when you make a control application, for example, air conditioner control or whatever, power control or whatever it is, you don't want much computing needs, right? So make sure that your selected microcontroller can do or meet the computing needs of your application. Now, in meeting computing needs, you need to check all these factors. In the sense, if you're worried about the speed of the microcontroller, this factor should be taken into consideration, because the reason is when you do computing, you obviously expect a speed, much speed in your processing, right? So make sure that the selected microcontroller has sufficient speed to execute your computing needs. And packaging in the sense how the pins looks like. There are two major packages which is called dual in package. That package IC you will be able to fix in a breadboard and you can write coding. And the other one is called QFN, which comes for surface mounted package. In the sense, you will not be able to connect it into your breadboard. It is not possible. So how do you choose whether it is a DIP or QFN? If you are a beginner, obviously you go with the DIP package, so that you can try the program or experiment the coding through your breadboard or general purpose board. If you are an expert, okay, you have the coding, but you want to replicate into a lot of samples or lot of let's say you have mass production. So in that sense, you have to go for QFN package. But if you're a beginner, you want to check whether the first product is working or not, then you have to go with DIP package, dual inline package, DIP package. Now, power consumption, obviously all the microcontrollers these days comes with less power consumption, so you don't want to worry about it. Then RAM space as well as a ROM space. ROM space is nothing but where you write the coding. So for example, if you have 1,000 lines of coding, you have to make sure that you have enough memory space at the ROM, right? So that your coding will sit into the ROM. And RAM is nothing but temporary data storage. In the sense, for example, if I want to store some songs, let's say I will store 10 songs today, and tomorrow I will overwrite another 10 songs, right? So RAM memory is nothing but temporary memory, which we can overwrite every time. So make sure your temporary data is or your RAM space is enough to store the temporary data. Then IO pins are those pins which talks to the external world. For example, if you have a microcontroller and you want to talk, I mean your microcontroller wants to talk with a motor, obviously that connection will be done through IO pins, input output port or input output pins. So make sure how many devices are connected externally to your microcontroller. Accordingly, you have to choose the IO pins. Then obviously cost is a major factor. And secondly, okay, I have selected a microcontroller. Okay, this is my microcontroller. I bought it. Okay, fine. Now, how do I write coding? So what software should I choose? Or where the software is available? Is it easily available in internet? Okay, so these are the second questions. So you have to see that the selected microcontroller will have the software support. Now these are the software supports you need: compilers, assemblers, debuggers, and emulators. Compiler in the sense which is nothing but a software which converts your coding into binary data, because binary data only what MCU can understand, right? So whatever coding you write, maybe in assembly level language or maybe C language, finally that has to sit like ones and zeros into MCU. So that conversion should be done by a software. So that software is called as compiler. Then assemblers is nothing but a notepad where you have to write the coding. And debugger is nothing but a simulator. So once you write the coding, you need to make sure that whether your coding works through a simulator. So you want to check the output and so on. So that you need debugger. And emulator is something like you can integrate your software and hardware. So this is a major factor nowadays people looks for. And third is very important thing is wide availability and reliability. In the sense, for example, you are a beginner, you have done a coding, you have developed an application, and now it is working. Now you want to order some 300, you want to sell some 300 pieces, okay, 300, or you have to do kind of mass production. Let's say you have to do some 300 pieces of mass production. So in that sense, you have to order, let's say, 300 microcontrollers. Now if you order from US or from anywhere outside the country, it takes more time to reach, as well as the cost is really huge, right? So you have to make sure that the selected microcontroller will have the supplier locally in your area. For example, what I used to do is whenever I write a coding, I used to select a microcontroller which is readily available in at least in Ritchie Street in Chennai or maybe in Bangalore, and I don't worry whether it is available in US or not, because it's not a fair idea to see that the IC is available in the US. Rather, you have to see whether the IC is available locally in the local market. So that's a very important thing. What many of the application developers used to think about, because they can't wait, because the customer will never wait, right? You have to, whenever you commit for a date, you have to supply the product, so that you have to make sure that the ICs are readily available in the local market. Right, now we'll see what is translator. Now I have a guy here, and this guy is saying, let's say, hello. Now my microcontroller cannot understand what is HELLO. Okay, so I need some kind of a translator to convert this hello into a format that microcontroller can understand. The format is nothing but ones and zeros. So I need to develop a data, or I need to develop ones and zeros, which has to say hello to the microcontroller, right?
Hello, I'm an Asian computer.
Okay. So translator is nothing but a software which converts your literal English into binary codes. For example, you used to write coding in assembly level language. Now, why we write in assembly level language? Because the programmer can easily understand what is move, what is jump, what is BSF, what is S jump, and so on. But you will not be able to remember ones and zeros, right? So that is the reason why we have created programming languages like embedded C or assembly language or whatever it is. But this is for you, right? I mean, this is for you. But At last, the programming go and sit in my MCU, right? It has to go and sit by MCU. The task should be done by MCU, not you. So in the sense, these codes or these instruction sets should be converted into a format which can be understood by MCU. So similarly, when you write coding in C language, where you have if, else, while, and so on, and that also should be understandable by MCU, right? So we need a software support to convert whatever the assembly level language or embedded C into a format of ones and zeros. So we have a lot of softwares. One of the software is Microvision 5, or you can also use MP Lab, ASM. So MP Lab ASM is a software which converts the assembly level language into binary format. Okay, this is the binary format. And if you are writing coding in C, you need something called MPLAB XC compiler. Okay, C compiler, which has an inbuilt debugger as well as assembler, and which converts your C coding into ones and zeros format. Right. So these are called translators or softwares which converts your assembly level language coding into your ones and zeros, which is understood by MCU. And if you're writing coding in C, then we need MPLAB XC compiler. And these products are from Microchip. Okay, whatever I am teaching here is exclusively for Microchip family. Now we'll see what are the pros and cons of assembly level language coding and embedded C coding. If you go for any embedded C training centers, including big corporate training centers, they used to say that embedded C language is more efficient than assembly level. It is not so. The reason is the best language is assembly level language, because the reason is it is more efficient. And why it is more efficient? Because this language is written in such a way that it is very close to the heart of the microcontroller. Heart of the microcontroller in the sense architecture of the microcontroller. So this coding is, our assembly level language is a language which is really close to the architecture of MCU. So it is really efficient by default. But embedded C coding is not efficient. I don't say it is not efficient. Its efficiency is based on the compiler ability. What is compiler? Compiler is a software which converts your C coding into a format which is understood by your MCU. If the compiler is poor, inefficient, you will be writing some coding. This guy will not find a bug, and that coding will directly sit into your MCU, and MCU will not work. We have witnessed a lot of cases like that. So efficiency of embedded C language is purely based on how good your compiler is. Okay. And understanding of assembly level language is really easy, but people used to believe that assembly language is really tough and embedded C is really easy. But that is perception. But I don't say, I used to say assembly level language is a better understanding. If you can understand assembly level language, you will be able to understand the architecture of MCU easily. Or in other words, if you understand the architecture of MCU properly, then only you will be able to write coding into assembly level language. And that is the reason all the training companies over in our country, they used to write only in embedded C, because the reason is the trainers are inefficient to understand the architecture of MCU. If they are able to understand the architecture of MCU properly, they can easily write assembly level language. And you can even check the coding which we are learning today. You go and type whether this coding is available in assembly level language or not, in the way what I have written. It will not be there, but you'll get the same coding in embedded C. Right. Now, what are the proficiency or steps needed to become an embedded engineer? In the sense, what are the things you need to know before writing your coding, or to write a program, or to execute a program into MCU, or to develop an application using programming language? What are the things you need to have in your hand? The first thing what you need is you need an assembler. Okay, assembler in the sense a place where you need to write the code. And once you write the code, obviously you want to compile the code. Okay, so compiling code in the sense you need a final conversion which is understood by the MCU. Then you want to test the code, right? So you need a debugger. And finally, you want to flash the code into physical microcontroller or physical hardware. Okay, now your coding is sitting in the software, but exactly the coding has to go and sit in the physical hardware. So we need a kind of software as well as hardware support here to flash the coding into a physical MCU. So these are the stages where we need to have exposure to become an at least a beginner embedded engineer. Now we'll see components of a programming structure. I mean, when you write a program, or what are the essential components available in a program? So if you see the program is nothing but sequential. For example, if you take human beings can do multitasking, right? If I give a vada, if I give a cup of coffee, if I give a cell phone, they can do all the three things at a time, single time, right? You can talk with someone by having your juice and tea, but microcontroller can also do multitasking, but it can do task wise. Task 1 first, task 2 second, task 3 third. That means first you have to eat vada, then you have to have coffee, then you have to talk over phone. Okay, so these tasks are defined by the programmer. If the programmer wants to eat first coffee, then he says the task 1 is go and have coffee, and then come and talk to over phone, and then come and have whatever it is. So in the sense, even microcontroller can also do multitasking, but it can't do multitasking at instantaneously. Rather, it can do task by task. Okay, and the task is defined by the programmer. Okay, which task to be done will be defined by the programmer. So that is what we call sequential programming. So if you take a program, if you write a program, you will have a component called sequential, because you will write in task by task, task 1, task 2, task 3, and so on. And next one is a decision. Decision in the sense, somewhere you go and stuck and you say, should I do this or not? The answer for should I do this or not will have two answers, yes or no, right? So that means there you are taking decision. So obviously a program will also have a decision loop. And sometimes you would love to do a task repeatedly for forever or so many times. So that we call as iteration. Okay. So if you take a program, it has three main components: sequential, decision, and iteration. Sequential is nothing but task by task execution. Decision is somewhere you want to go ahead or not, you want to know that. And sometimes you want to do a task forever. Okay, something called while loop in your program, C programming. So that is called iteration. So these are the main three components in a program structure. Now we'll see a sample program first to generate a sine wave. So let me show you how to generate a sine wave. Right. Now, what I need in order to generate a sine waveform is I need some samples. Okay, I need some samples. I'll tell you what is the sample means. For example, you would love to generate a sine wave of 500 hertz, right? Let's say. Now, you need to create some samples of one full cycle. Now, how should I create or generate samples? You have a sine function called sine 2 pi fnt. I hope you would have studied sine 2 pi fnt. Sine 2 pi f. F is the frequency, desired frequency. And n is the number of samples, whether sample 0, sample 1, sample 2, sample 3, sample 4, and so on. And t is the time interval, because you have lot of samples, there will be a time interval between two samples, right? That time interval. Okay, so in this case I have a time interval of 80 microseconds. So in the sense, if I take samples in between 80 microseconds, in order to generate a 500 hertz sine wave, of one cycle, I need nearly 26 samples. Okay, let me repeat. The question is, I need to generate a 500 hertz sine wave. Now I am going to take some samples. Okay, so when I take some samples, I need to know what is the interval of the sample. Interval in the sense the time duration between two consecutive samples. So the time duration is called a sampling time, which is 80 microseconds, which I have taken. You can take any time, no issues. If I take 80 microseconds, for example, let me do in calculation. Let me take one. Let me pick a calculator. Okay, 1 second. Okay. So here, let me play it. Here I am typing 0.002 in the sense 2 milliseconds. What is 2 milliseconds? The inverse of 500 hertz. Okay, 1 by 500 is 2 milliseconds time period. Okay, 2 milliseconds is the total time period which I want to develop. If I take 25 samples, okay, if I take 25 samples to create a 2 millisecond waveform, so 2 milliseconds divided by 25, let's say, I'll get 80 microseconds. So in the sense, I need 25 samples at least to create one cycle of 500 hertz waveform if I go and pick samples at an interval of 80 microseconds. Okay, let me show you again. Let me take the samples so that you'll be able to see. Let me move forward. Okay, now you could see a lot of samples. So that is the formula, sine 2 pi fnt. So I got some samples. So if you see how many samples, I have nearly 25 samples. Okay, and you see the waveform here, I'm getting one cycle. Okay, so what I have taken is I have drawn a 500 hertz sample, or I have taken 500 hertz waveform samples of 25 numbers to create one cycle of sine waveform. Okay, now what I'm going to do is this is an Excel sheet. Okay, this is an Excel sheet. I'm going to develop the sine waveform only using these numbers, sample numbers, and I take the sample numbers into my coding, and I'm going to develop a sine waveform like this. Okay, okay, let me show you how to do it. So let me show in software. So before that, you need to understand another important concept, that you can see some numbers here, right? Samples. In these samples, you can see 0, 0.248, 0.48, and the positive value is 0.997, and the most negative value you can see minus 0.9982, and so on. But if I feed these numbers into my microcontroller cannot understand this. So what microcontroller can understand is anything you write between 0 to 255, because we know microcontroller if it is an 8-bit microcontroller, it can understand anything between 0 to 255. So whatever the samples you get here, you are supposed to convert into a format of 0 to 255. Okay, so 0, 0, 0, 0, 0, 8 zeros and all 8 ones. So as I said, ones and zeros format, binary format. So the idea is the samples which you have generated through sine 2 pi fnt formula, that should be converted into a format of 0 to 255. And this method is called as scaling method. So how do I scale it is, I know microcontroller can understand the minimum is 0, maximum is 255. In this waveform, what is the maximum value? Plus 0.99. What is the minimum value? Minus 0.99. So I will assign minus 0.99 to 0 and plus 0.99 to 255. So I will be able to generate all these numbers. Okay, so the simple idea is I'm going to convert the random numbers into a format of 0 to 255. That's it. And in my coding, I'm going to represent only these numbers, not the yellow shaded numbers, because MCU cannot understand all these steps. Okay, let me show in the coding. Okay, this is my coding. Here I'll tell you how I have done this coding. Here you could see some numbers, right? 127, 159, 188. Those are these numbers. which we have scaled to 0 to 255 format. Let me show you again. Okay, these numbers. So these numbers are here in the coding. Okay, so now how this coding works, let me show you through an animation. Okay, now as I said, I have to take lot of samples. Okay, in that case I have taken 25 samples. Here I am showing in the demonstration or the animation just 10 samples. Okay, so sample 1, sample 2, sample 3, sample 4 are the locations, and these are the samples. Whatever I am showing here is the samples. So this is one sample, this is another sample. It looks like a brick. When you construct a house, you will not be able to construct a house using a single block, right? You have to use small blocks. So in order to construct a waveform, we are taking small bricks, which are called as samples. So this is one sample, this is another sample, this is another sample, this is another sample. So there are 10 samples like that. Now each sample, I'm going to assign an address, because I need to inform my MCU where I have stored the sample, right? So for example, this is my street number. That's the reason I kept is 34/1. So 34/1 will be the address of, to pick the first sample. 34/2 will be the second address. I mean, as the second address to pick the second sample. 34/3 will be the third address to pick the third sample, and so on. So in other words, the programmer need to make sure that where you are writing the sample or where you are storing the sample, you need to inform your microcontroller from where you are going to, from where you have stored your sample. For example, in this case of 34/1 to 34/10, the starting address is 34/1, right? So microcontroller will come here first 34/1, then pick the first sample, then automatically increment it to the next address, and so on until it reaches the 10 sample, right? So as a programmer, what you have to inform is, you have to inform your microcontroller that I have stored samples, the starting address of the sample is 50, and total number of samples is, let's say, 100 or 10, whatever it is. Okay, so before you write the coding, you have to make sure how many samples we have and we need to collect. Okay, for example, in the Excel sheet I have shown you 25 samples. So you have to make sure that you are collecting, or your MCU is collecting 25 samples, because if you are not collecting 25 samples, you will not be able to get one complete cycle, right? So that is the reason you have to make sure that you are able to collect all the 25 samples without a miss. And then what is the starting address of the sample? Okay, I have a lot of samples. What is the starting address? This is the starting address. For example, 34/1 is the starting address. Then once fetch the first sample from 34/1, I need to increment by finger to go to 34/2. That means you have to write your tell your MCU that I will show you only the first address. The next address you have to do automatic incrementing. Okay, you do automatic incrementing and go and fetch the second sample. I will show you only the first address. So that you have to mention in your coding. And then you have to tell your microcontroller that you have to collect all the samples. Okay, so you have to make sure that you are collecting all the samples. So in the coding, we have to do something so that we need to make sure that MCU is collecting all the samples. Okay, so with this, we need to write the coding. And I will show you the how it actually works in animation format. 1 second. Let me play it again. So up to this, you have seen. Okay. So let me delete all these address. Now, first you need to have a countdown. For example, you are going to collect 100 samples, let's say. So your countdown will be 100. Initial countdown will be 100. Okay. Now, why I need countdown? Because if I have countdown, then only my MCU can understand that I have collecting all the samples or not. I'll tell you what it does in order to make sure that it has collected all the samples. So let's start the animation. So first, we have given the starting address 34/1. Okay. So MCU will go and indicate, or it points its finger to 34 bar 1. Okay. And it fetch the first sample. This is the first sample. Now first sample comes here at the output to create the waveform. This is the first brick of our house. Okay. And once I collect the first sample, what should I do? I need to reduce my countdown because I have collected 1, right? So now the countdown is 99. Now what I have to do is I have to, or the MCU has to automatically point the next address. Okay, next address. So 34 bar 2. Now it has to fetch the second sample. So second sample will come at the output. Now your countdown will reduce to 98. And now your finger will point to sample 3. Now it picks the sample 3 and construct the waveform. Now your countdown gets reduced. Now your finger will look at sample 4 and take the sample. And it goes like this. It goes like this. Okay. Finally, when you pick the last sample, then this countdown will become 0, right? So then you will be able to understand that your microcontroller has picked all the samples, right? So this is what we are writing in the coding. Let me show you the coding. Okay, this is the coding. And here, these are the samples. Okay, this 50 is the starting address, similar to our 34 bar 1. And this is the countdown. 26 is the countdown. Okay. Okay, so this is the countdown value. And as I said, it has to automatically point the finger, right? So that is what this code. A data pointer is there. The data point is nothing but a finger of microcontroller. And the countdown reduces, right? This is what this DJ is a DJ in the sense it is decrementing its count from 26 to 25, 24, 23, 22, and so on. So once it reaches 0, we will stop it. Or maybe we will continue to have the next cycle, whatever it is. Okay, so this is the coding. Let me show you the waveform. Yeah, this is the waveform. So now you can see something like we built a sine wave using some bricks, right? So bricks are nothing but the samples. So here you could imagine like the sine wave doesn't look so pure, right? It looks like kind of how we construct a house, a brick kind of look, right? So because the reason is we have used only 25 samples to construct this waveform. Okay, so if you count the number of samples from here to here, it will be 26. I mean, from 0 to another 0, it is 26. From 0 to the maximum negative, it will be 25 samples. So 25 samples will take into one cycle. And if I measure the frequency, I'll tell you whether we are getting 500, because 500 is what we need. So if you measure one cycle, you can see 496.524. It is close to 500 hertz. So we are really happy with that. And if you would like to create a pure sinusoidal waveform, what you can do as a programmer is you have to go with a lot of samples. Okay. So here I don't have 25 samples or 26 samples. I have nearly 101 samples here. So when I go with 101 samples, then obviously my waveform looks like this. So it's a pure sine waveform, right? So if your sampling is, if you have more samples with in your hand, you can create a pure waveform. So that's the idea, right? Now let's look on how to generate tones, music tones. Now to generate music tones, what you do is you first go to internet and see is there any music notes available. Okay, for example, if you want to play Sari Gama Padani, each note will have a certain frequency, right? So for example, this is a note which I have in a keyboard. Okay, the keyboard tones. So one tone is at 523 hertz frequency, another tone is 554 hertz frequency. So each and every tone, if you see, it will be different frequency. We know songs are nothing but frequency, right? So each and every tone is nothing but a frequency pattern. So I have 24 tones over here, 24 tones. All the tones have different frequency. So that means the all the tones looks to be different tones. Now, how to do coding or how to generate these tones is very simple. That you have to create a square waveform. You have to create a square waveform, okay, like this, of the particular frequency. For example, if I do want to have this tone, 520, a tone of 523 hertz, you have to develop a square waveform of 523 hertz. 523 hertz. So in the sense, you have to first make your port pin high, okay, and then take some delay, okay, delay, and low your port pin, and then take some delay, okay. So if you see how much time this is frequency in terms of time, 523 hertz is similar to 1911 microseconds. So this total time will be 1911 microseconds, 1911 microseconds. So as I said, I need a half delay here. Okay, half time I need a delay and another half time over delay. So what you do, you divide 1911 divide by 2, you will get 955. Okay, so 955 microseconds a delay here and 955 microseconds delay over here. So this will enable you to create a square wave of 523 hertz. Now you can do this delay in two types. One is an amateur type, is you can write delay, or if you are writing in C coding, you can call a function delay of milliseconds, whatever it is. But a professional way of doing is you can use the timers available in your microcontroller. So if you have timer in your microcontroller, you have to create, or you have to know what timer value should I write in the timer registers so that I will get 523 hertz. So that you have to study about timers, then only you will be able to develop it. Okay, so you study timers. There are two registers in timers, timer H and timer low. You have to put some values over here, I mean proper values over here, so that you will be able to generate a frequency of 523 hertz. So similarly, all the way you have to generate different frequency. Now let me show you the coding. Okay, this is the coding. As said earlier, the same thought. Okay, so this time this is the samples you have. 68 252. I'll show you the Excel sheet again. 68 252. Yeah, you can see 68 252, 122 252. So I kept the same values here. Okay, the samples. Okay, so these are the samples which are going to create the delay. And I have used some timers. So these are timers, timer registers. Okay, you use timers, so that look professional, more professional. And as I said, you have to make a port pin high and port pin low, right? So this is the port pin which I makes high and low. Okay, port 2.5. So if you do like this, you will be able to generate different tones. I'll simulate the different tones. I am not sure whether you'll be able to hear it. Let me play it somehow. I've put the coding inside my MCU here. This is Proteus software. So I kept the coding here. Now let me switch on this switch, so you'll be able to hear. I hope you'll be able to hear some tones, different tones. Okay, I kept all the 24 tones in a single output pin. So let me play it so that you can hear. So let me, this is the total tone, all the combined effect of all the 24 tones. Now if you want to have single tone, let's say, Okay. So you can this is the tone. This is the keyboard tone actually. So you can generate anything if you want to make a song. Even you can do it. It's highly possible. Okay. So let me close this. Okay, let's come to the final session. How to do a MP3 song, or how to sample an MP3 song. So similar to that, what we have studied in to generate a sine waveform, we need samples, right? So similarly, what I have taken is I have taken some portion of song and I have converted into some numbers using MATLAB software. So if you feed a song in MATLAB will give you some numbers. So here I have lot of samples, nearly 2000 samples I have. Lot of samples are there. Okay. Yeah, nearly 2000 samples are there. Now, as I said, you will not be able to feed all these samples directly into MCU. You have to make a format that MCU can understand, which is nothing but 0 to 255. So whatever the samples you get, you have to scale it, or you have to do kind of offsetting and convert into 0 to 255 format. So this is the final format. Okay, this is the 255 format, which 0 to 255 format which we have done. Now, once you make this format, you need to make sure that this and this are correct, because you have to do the proper scaling. Otherwise, your waveform will get, your output will be different waveform, right? So what you have to do is you select all these samples you receive from MATLAB, go to insert and take the graph and see the graph. So you can see this kind of waveform. Now what you do is, let me put it here. You take the scaled value of 0 to 255, okay, and go to insert, take graph, and take the graph, and see whether these looks to be similar or not. So if it is similar, your scaling and your offsetting is in the format of 0 to 255 is correct. Okay. So what I have done is I have not taken all the samples. I have taken only few samples here. And I'm trying to replicate the first few samples. So this is the input waveform. Okay, so I expect this kind of output from a MCU. So let me show you the coding. Yeah, here I have all the samples. Okay, you can see the samples here. Nearly 2000 samples are there, but I'm going to replicate only a small portion. Now, when you put all these samples here, for example, you have 2000 samples. Now, assume that you are going to pick a microcontroller. What criteria you will think? I mean, in that criteria, we have studied a lot of the three criteria. In that criteria, to have these many samples in your code, what factor do you think and properly select the microcontroller? Put your answer in the chat box. Let me see. Did you get my question? You have 2000 samples to put in your code, okay, and you know very well that before choosing your microcontroller, let's say you know that your coding needs 2000 samples. Let's say now you are going to pick a microcontroller. Which one you would love to I mean, which factor or which criteria you love to give more importance, or you give more importance to pick the proper microcontroller? You have 2000 samples to put in your code. So what factor do you think while selecting microcontroller? Anyone, please? Very good. Memory in the sense, which memory, RAM or ROM? No, not RAM. It is ROM. ROM is nothing but code memory, right? RAM is nothing but temporary data. This is not temporary data. This is what I'm writing in my coding, right? So this is going to be permanent as long as I delete this coding, right? So this is going to sit in the code memory or ROM or program memory or whatever it is. Both are same. All the three are same. Program memory, code memory, ROM. So let me run this, and you can see at least a small portion is coming or not. So let me build it, translate. Let me see if there is any error. I don't think so. There is error, and let me no error. Now this is a debugger. Debugger is nothing but simulator, as I said, software simulator to see your code. And let me run this code. Yeah. Now you could see this portion, right? This portion. Okay. So this portion looks to be similar to that of this, right? Our raw data. I mean this data, this raw data, a sample of a small portion of this data, right? So this and this is the original waveform which I have sampled, and what I have done is I scaled into a 0 to 255 format, and through my coding I am going to reproduce it. So if you see one portion of this output, this looks very similar to the input waveform or the MP3 song. I'll show you in the PPT both of the waveforms, so you'll be able to understand. So this is the waveform you have seen now, and this is the clipped. I have just cut the waveform from here. So this is your original MP3 song clip, and this is the reconstructed waveform. So both looks to be same, but there will be little bit noise. You can arrest this noise using Audacity software. So you can do kind of low pass filtering or high pass filtering depending upon what you need. So so this is the idea. So in this case, what we have done is we have taken an MP3 song, we have converted the song into sample format. So these samples you can convert through MPLab software. So these samples are just a raw data which MCU cannot process it. So what we thought is we have scaled it into a format that MCU can understand, 0 to 255, and we put in your coded memory or program memory, and we write the coding as per the similar logic of how we generated sine waveform, and then we got the same sort of waveform output, right? So what is the benefit? How do you interpret this is a playback? So this is playback because the reason is what I am doing here is I am just saving the song, right? These numbers are nothing but an MP3 song. So I can play back the song whenever it is needed because the song samples are stored somewhere in the program, right? So this is called playback system. So you take an MP3 song, convert into samples, put it into the memory, store it. Whenever you wish to hear the song, just play it. All these samples will be converted into a waveform, and you can hear the song, right? So this is the idea of audio playback system. So I hope that you have understood some sort of idea. Let me do a quick recap what we have learned. So what we have learned is we have seen what God has given, some kinds of measurements, and we said engineering means creating purposeful utilization of these measurements. And when I called this guy and asked his purposes, he said, I have a lot of purposes. And to implement all these purposes, we invented technology, and technologies has started from the physical parameters, and now it is there at digital world. And we have seen microchip microcontrollers, and we said what is the importance or why we give more importance to pick microchip products. And then we have seen what are the criteria to select an MCU as an embedded system engineer. What are the things you need to consider? So we have seen three major factors. And then we have seen what are translators. Translators are nothing but which converts the programming language into the binary format which is understandable by microcontroller. And then we have seen the advantages and disadvantages of assembly level language and embedded C coding. And we said both are good, but still in embedded C you have to be more reliable with the compiler you use, but you don't want to worry about the compiler capability when you write coding in assembly level language. And what are the things I should know before I write a coding or before I develop an application? So we need to have exposure in all these 4 items. And what are the components of a program structure? A program structure will have mainly 3 components: sequential, decisional, and iterational. And then we have seen how to generate a sine wave of desired frequency. And we also have seen how to generate a pure sine waveform by increasing the number of samples. So this is the animation which we have seen. Then we thought to develop a lot of music tones. So we take some list of music tones from internet, and we were looking at its frequency, and we were generating that frequency using timers. And we have seen or we heard that music tones too. And finally, we did sampling of MP3 song. So we got some samples from MATLAB, and then we did some offsetting, because offsetting is needed because the raw data cannot be understood by the microcontroller. So we need to convert in the format of 0 to 255, and we put it into the coding memory or code memory ROM space, and then we called the coding whenever it is required, so we could see the final waveform. And the final waveform looks similar to that of the input waveform or the input samples, right? So this is the idea of playback system. I hope you have enjoyed the session, and if you have any doubts, please put your questions in the chat box. Let me hand over the mic to the coordinator of this program.
Sir, thanks a lot for your great information about the session, sir. So thanks a lot for accepting our invitation, sir. There are 2 questions, sir. So if we take samples about 255, how to order the samples into 0 to 255?
See, you cannot take sample. You can take 4,000 or 8,000 or 10,000 samples. The idea is how do you offset it? You cannot offset beyond 255 because the data is an 8-bit data, right? For an MCU, for example, the MCU which I have taken, AT89S51, is an 8-bit microcontroller. 8-bit in the sense 2 power 8 is 256, right? So 0 to 255. So the data which you can send at a time is nothing but an 8-bit data. So even you can take 100 samples or 2,000 samples or 8,000 samples or 20,000 samples. But the idea is you have to do proper scaling and such a way that you have to bring to 0 to 255 format.
So the next question is, MP-Lab is an open software or not? How to get the software?
You have some trial version in. You just visit Microchip official website. You have a trial version for a month or 2 months. Trial version is available.
So that's all for the question Q&A session, sir. Thanks a lot for accepting our invitation, sir, and thanks a lot for it, sir.
Yeah, welcome.
So the feedback link has been sent to your chat box. So I'll be sharing the feedback link once again in the window. So this is the feedback link. So see my slide, and I am presenting it. So the next session will be on next Sunday, same timing, or 6:30 to 7:30 it will be. So the next session is on impact of IEEE in the individual. So any other queries? Any other queries? And the feedback link will be open till 6:50 p.m. So please fill it as soon as possible. Don't share the link. Komal Raibagi, no sir, we will get an mail about it. Yeah, you will be getting the mail about which thing you are asking, about the certificate or the next event. So please chat in the chat box.
Dhanush,
Yeah, yes, it's me.
Dhanush, inform them certificate will be received through mail once you fill the feedback form.
Yeah, sure, sir. Yeah, sure, sir. So the certificate will be sent through the mail if you fill the feedback form. Within 15 minutes, you will be receiving the mail. So any other queries? So this is Dhanush Ganesh signing off from the event now.